All right, hello everyone. My name is Jeff Bryant, and today we're going to be going over the astronomical entity types for use in entity value. I'm one of the research programmers for Wolfram Alpha, so I'll be kind of guiding you on this tour through the universe, through the Wolfram language. These entity types that we're going to be talking about today have seen a fair amount of growth since they were first introduced in version 10 of the Wolfram language, and as of version 12, they've grown quite a bit. So what I'm going to do is kind of slowly go through this this page here. Let me just adjust things a little bit here, so that I have my slider here that I can see. We're going to be going through. Let me just widen this just a bit. We're going to be going through a number of different domains here on the marketing page that you see here. You can see that we've got data for nearly 20 related domains for space science and astronomy. This includes planets, moons, asteroids, comets, stars, and various deep sky objects, among others. We've got quite a few, almost 250,000 objects total. A lot of data spread over a lot of different properties. We've got static properties that don't change with time, as well as a number of time-dependent properties. We've got a number of domains that we actually have that we update the data behind them on a fairly regular basis. Typically, these are ones that, there's lots of new things either going up into the sky, such as in satellites, or lots of new discoveries that are happening right now, like with exoplanets, where there's ongoing satellites that are studying these things. And so what I'm going to do is take you down through this page real quick before we back up and look at the individual examples. The first row is mainly going to concentrate on the solar system. And then we're going to kind of zoom in a little bit. We're going to look at some of the mapping capabilities that we have for creating topographical maps using geographics in the Wolfram language to look at alien landscapes within our own solar system. Then we're going to move outwards from the solar system. We're going to start talking about things on stellar scales. We're going to go from comets, and then we're going to spread out into the exoplanets and stars. Talking about constellations, we're going to go out further into pulsars and deep sky objects such as star clusters. And then we're going to focus a little bit on space science. And these are areas that are going to involve things like deep space probes, satellites, manned space missions, and also astronomical observatories. Pretty much anything you can connect to astronomy or space sciences. But first, I'm going to back up just a little bit, because I want to make sure that everybody here understands how to use the entity value functionality that's been around since version 10, and specifically I want to show you how to use it for astronomy. Let's see here. I'm going to bring up a notebook here so you can see a few things that I'm going to show you. So first things first is, how do you use entity value? Well, the first concept to master are entities, and some of the other talks that we've given on version 12 recently have probably talked about entities in other domains. I'm just going to focus on the astronomy ones, and we'll start with a very simple one. One of the easiest interfaces to entities is with control equals. This is our natural language discovery mechanism. So you do control equals, you get an input box. You can type in something like Jupiter. Use arrows to get out, and it presents you with this yellow box. You've now got an entity. Now, entities on their own, there's not much you can do with an entity. It's just a symbolic representation for this concept. But you can then ask for a property. Example, textured surface. And you will get a three-dimensional object that you can rotate. So you can see what Jupiter looks like with the textured surface here. Includes a great red spot here. And there's all kinds of other properties that you can do in this domain. So for example, you can change this to mass. If you want numerical data, you'll get the mass of Jupiter in kilograms. Also radius. You can also do multiple properties. So if you want both the mass and the radius, you can just provide a list here. You get both quantities as you requested. So these are the basics of entity value, and that's going to be, this is shorthand for entity value. The long form is entity value. You can put the same entity that you have up here as the first argument, and the second argument of entity value is just the property that you want. So this gives you exactly the same thing that we got up above. This is just shorthand notation. So this is the curried form up here and this is the full-blown entity value form. These are going to be the basics of the examples that I'm going to show today, so I just wanted to start here with some of the basics before diving right in. So if you look at the first examples here, we're going to dive into the planets first. And you can see that we've got a number of examples here where we make use of some of the data that we've added since version 10 and kind of built up since then and led to what we have now in version 12. You can see that, as I showed before, we have a textured surface property. Here we're using entity value to actually query for the planet, all the planets. That's why the first argument there just is the entire domain. And we're getting the textured surface and the obliquity for each of the planets. Now, I can evaluate this. It's like we did on the website there. You can see that it downloads the values. And then, let's see here. We have a couple other lines of code that we can use. I'm going to define this special function. It's just a graphics 3D using the Mathematica Wolfram language 3D scene language that just rotates a cylinder according to a certain obliquity. And we're also making use of the surface that we queried for. Now I can create a grid of these that takes the data, which is defined by P data here, and generates the graphic that we see on the website. Takes a second to render these. And there you go. Each one is actually a 3D graphic that you can rotate, but by default, they're all tilted with respect to their relative obliquity. So you can see how their axis is tilted for each planet. So Earth, you can see, is tilted 23.5 degrees. It's very similar to Mars. But you can see Uranus, for example, is tilted almost entirely on its side. Neptune is also tilted similarly to Earth. Jupiter's just barely tilted. It's only got a slight tilt. All right. So these are good examples of static things. These are things that don't really change with time per se. The obliquity of the Earth, for all intents and purposes, is a static property. It's about 23.5 degrees. It does change on very long time scales, but this is just a nice static example. But now I want to move on to something that shows some of the data we have that changes with time. And so for that, we actually have to make use of what are called qualifiers. Qualifiers are ways that you can specify dates, locations, things like that, that basically modify the property in question. So here you can see that I'm asking for the altitude. This is the celestial altitude, so the angle above the horizon from my current location. This is asking what qualifiers does this particular property take? And you can see that it takes both date and location. We can make use of that here. So here I'm saying, give me the planet Jupiter. This is just the input form of an entity. If I highlight that and do Shift Control Enter, it evaluates it in place and it turns into the yellow box we saw before. The second argument is an entity property. Now, when you want to use qualifiers, you need to use the full entity property box here, not just the string form I was using up above, like altitude. So you have entity property. The domain is planet. That's the altitude property. And we want to specify the location for Chicago. So this is the observation location. So the altitude of Jupiter right now in Chicago is minus 62 degrees. So Jupiter's well below the horizon from Chicago. We can also specify not just the location attribute, but the date attribute. We can say now, which is the default. So this is for, since I didn't specify in this case the location, it's using my current GeoIP location. So now I'm in Champaign, so the value you get is a little different. We can use qualifiers with date attributes. This is a shorthand for the date attribute. It's called dated. You can wrap this around a property and specify a given date. You can say, what is the apparent magnitude, or how bright is Jupiter right now? You can see that it's minus 2.54, so it's pretty bright. Jupiter's a bright planet. And we can take this a step further. I'm going to actually break this up just a little bit for readability. I'm going to define a start date and an end date. I'm just using date objects that are used in the Wolfram language. Here we've got an entity value call, and I'm obtaining just the visible planets to the naked eye. So here you can see Mercury, Venus, Mars, Jupiter, and Saturn. And here you can see the second argument of entity value. So I've got a list of entities. The second argument is a table of dated properties. And I'm going to actually generate a table of dates from the start date to the end date. So here the start date is January 1st of this year to December 31st. So I'm going to plot the brightness of all the planets. Oops, forgot to evaluate the dates. That would help. Let me just wait for a couple seconds here for the data to be downloaded. And as soon as you get that data, you can actually do a plot of it. So here we're using date list plot to plot the magnitudes from the start date to the end date, and a couple new options, including scaling functions to reverse the y-axis. Brightnesses in astronomy are kind of backwards, so brighter values are higher up. So that's why I've used scaling function goes to reverse. And here you can see how the brightness of each of the planets changes throughout the year using date list plot. So here you can see where we've created a visualization using the data obtained from, in this case, the planet entity type for each of the visible planets. All right. Now, something else we can do, I'm going to move on here. We've got the ability, this is something that's new in version 12. We have increased capabilities for using callouts. So if you want to annotate a lot of your graphics, you can actually do that. And this is a nice example. So I'm just going to actually click on this. That's a nice feature of the website for these examples. You can just click on them, and then you can go straight in here and paste. And in this case, what we're doing is for Jupiter, we're getting the atmospheric composition, and we're actually getting basically the average. And we're going to specify a labeling function just for convenience here. There is default labeling functions. They may or may not lay out the way you want. They do a pretty good job in general, but sometimes cases like this where you have kind of an extreme edge case here where you've got a lot of data in a tiny little area, sometimes it helps if you manually specify a labeling function, and you can make this as simple or as complex as you want. And you can actually see that we can label all the atmospheric constituents of Jupiter. It's mainly hydrogen, a little bit of helium, with a whole bunch of trace elements. Some stuff you probably wouldn't want to breathe in. So Jupiter's not a fun place to visit. All right, moving on. We've got the solar system moons. This is just kind of an extension to things that we can do for planets as well. Here you can see that we have a number of moons. I've just kind of selected some here. And we can just paste those in here. And we can create a graphics grid, just toggling back and forth between the marketing page and my notebook here. We can get the textured surface for each of these moons and align them in a grid to see what each of these moons looks like. And you can see that we can reproduce what we've got on the marketing page. Each one of these examples has all the code that you need to reproduce this. So if you wanted to play around with these as a basis for your own experiments, feel free to do so. Here's one where we're actually plotting more data, not just a picture, but we're actually, for every planetary moon, we're getting the orbit period and the semi-major axis. And we're generating an entity association. So this takes each entity and associates it with its value. And then we can do a list log plot of that. And when you do that, it takes a second to download the data. When you do that, you get an interesting plot that has the moons for each planet lying along diagonals. And each diagonal corresponds to each of the planets. This is actually Kepler's third law, kind of visually represented. Each planet has different mass, so it causes differences in orbit periods, and the relationship between orbit period and semi-major axis is kind of the basis of Kepler's third law. All right, moving on. Some of these examples are going to take a little longer, so I'm just going to kind of walk you through the page because the amount of data that we're presenting would take quite a while to download, and it's kind of beyond the scope of this presentation. So I'm just going to kind of go through here what we're doing here. Kirkwood gaps are something that we see in the asteroid belt, the primary asteroid belt between Mars and Jupiter. And because of Jupiter's influence on the asteroid belt, it actually causes certain areas within the belt to have gaps in it. And these gaps are called Kirkwood gaps. And we can actually represent or see these by querying for things like the semi-major axis of objects, as I've done here. And what we're going to do is we're going to get the semi-major axis for all minor planets, but we're going to put a restriction on it. And we're going to say, give us only those that have a semi-major axis between 2 and 3.5 astronomical units. This will limit us to the primary asteroid belt. And once you get that data, you can plot a histogram of it. And we're doing, by doing a histogram, you're essentially seeing how many are there at a given distance. And so what you can see is that here around 2.5 astronomical units, there's a big giant dip. This is one of the biggest gaps in the, one of the biggest Kirkwood gaps within the asteroid belt. Then they go back up very quickly as you move outwards in the solar system. It dips back down. Some are more prominent than others. There's another big one here. And so these are all due to what are called orbital resonances with Jupiter. And this basically, if you divide Jupiter's orbital period by the orbital period of the asteroids at this distance, you'll find that they have integer ratios, very small integer ratios. So like 1 to 2, 2 to 3, things like that. And this actually causes instabilities, and objects there, if they make it into that zone, will get perturbed out. And you'll find them either on either side of it or just totally tossed out altogether. And so we can actually figure out where exactly these orbital resonances are by, first of all, determining Jupiter's orbital period. Here you can see I'm doing that, and I'm saying give it to me in years. We're making use of Kepler's third law here to associate the semi-major axis as a fraction of Jupiter's orbital period. And then we're generating a set of resonances by essentially taking the small fractions, essentially, and associating that with what semi-major axis would that be as a fraction of Jupiter's orbital period. And once we have that data, we can create some annotations, some arrows, and we can annotate the graphic that we generated up above. And here you can see that we've actually got the 3-to-1 orbital resonance. So this is asteroids that orbit 3 times for every once of Jupiter. Here's one that's 8 times for every 3 of Jupiter. 5 to 2, 7 to 3, 9 to 4, giant one at 2 to 1, and much more small ones out here as you start getting toward the tail ends of the asteroid belt. So there's not as much data being presented here. Anyway, so let's move on from this. Something else that we can do, and this does take advantage of something that's new in version 12, is we can actually do in-body simulations of asteroids. So in this case, what I'm actually doing is I'm essentially using the data from minor planet data in this case, or actually the entity type minor planet. Minor planet data, the symbol under the hood is basically just using entity value. But here we're focusing on the entity type directly. So here you can see that I've got the Sun and Jupiter. I can take an asteroid, for example, Hilda, and I can obtain several properties, just as we've done for some of these other things. I'm getting the orbital period of Jupiter. We're going to use this as a duration for our simulation. And I'm going to obtain data for a subset of the asteroids. These are called the Hilda asteroids, and these have some interesting properties that we want to visualize. And these essentially are, they have an orbital period of 2/3 that of Jupiter. And I'm putting a little bit of a fudge factor here. I'm actually getting, rather than just exactly 2/3 orbital period, I'm doing 0.9 to 1.1 times 2/3. So that's just, a little bit of a fuzzy definition of 2/3 the orbital period of Jupiter. And then we're going to restrict the inclination to those that have about 20 degrees or less than 20 degrees, and eccentricity less than 0.3. So relatively circular, not highly eccentric. We're also going to get the Trojan and Greek asteroids. Those essentially have the same orbital period as Jupiter. We're going to set a start date here. This is May 9th, 2018. Define some utility functions. Here, the XYZ is just calling the entity value on a given asteroid, and it's going to get its 3-dimensional coordinates and heliocentric coordinates for a given date. We're also going to define the speed to be essentially the difference between 2 different XYZ positions divided by 1-day increment. We do some additional data extraction, define some data, and we're going to construct the arguments needed by in-body simulation in version 12. This is usually done in the form of an association. So here you can see the Sun. We define the mass, the position, and the velocity for the Sun. We do the same thing for Jupiter. And then here I'm doing a table to do this for all of the Hildas that we extracted up above. We're just, for simplicity, we're going to we're going to give all of the asteroids the same mass. They're relatively negligible compared to, say, the planets. And so we're just going to give them something that's kind of just generally in the ballpark of what an asteroid mass might be. We're actually, to speed things up for the simulation, we're not doing a true in-body simulation. We're essentially doing in 3-body simulation. So we're going to give them all the same mass, but we're essentially going to ignore the mass of the individual asteroids because they don't really perturb each other. Here you can see the position and the velocity is extracted for those as well. We're going to define the potentials as such, just with some more rules. Here's where we actually construct the in-body simulation. We're using pairwise potential as its argument, feeding in these potentials that we specified up above. Continue. And then here, you can see one frame from the in-body simulation, essentially what it looks like initially. So here you can see in purple, these are the Trojans and the Greeks. Here's Jupiter sitting out here. Obviously, it's been greatly enlarged to scale. This would be much smaller. It wouldn't be much larger than this. And these are obviously drawn up much larger than their true size. And the sun here is a reference. Now, but we can actually animate this. And this is the result of the in-body simulation run over an entire Jupiter orbital period. You get some pretty cool dynamics. The Hildas, the ones that have about 2/3 the orbital period of Jupiter, they move on basically circular orbits or low eccentricity elliptical orbits, but they actually stay as a group on this triangular path, and they kind of merge up with the Trojans and the Greeks, which are shown in purple. So some interesting orbital dynamics can be shown using some of this data that we've got here. All right, let's move on. Now that we've looked at some of the planets themselves, I want to zoom in and show you some of the mapping capabilities that we've actually incorporated so that we can leverage some other features. It still uses entity value under the hood, but in combination with geographics. So here you can see we basically have just specified Olympus Mons. This is another entity type that we have. So I'm just going to copy this, put this into my notebook again, just to duplicate what we just did. So you can see the entity being used here is in the domain solar system feature, and it's Olympus Mons on Mars. And when you feed this and you give it a geomarker around there to say what you want to do with it, you can use geographics to plot this, and you get a map of Mars showing you where Olympus Mons is. And this is great for a global map, but it kind of gets lost at this scale. So it's there. It might be kind of hard to see it, but it's the largest volcano in the solar system. And we can actually make use of some relief plot data. As you can see here, you get some much more interesting as if we zoom in here. Get what we've got on this. So once again, we've got Olympus Mons on Mars, and we're just saying geographics, georange, but notice we're using geo background goes to relief map. I've zoomed in with georange, so we're not looking at the entire map globally. And this actually uses elevation data that we have for Mars to see. This is vertically exaggerated, but you can see Olympus Mons. It's even got some kind of old ancient lava flows that have kind of flowed out from it. It's not active anymore. With some of the other surrounding terrain, some other volcanoes and stuff that are near Olympus Mons. You can also zoom in further, and this is not using relief. This is just Olympus Mons itself. But you can see it's a giant shield volcano. So it's actually kind of similar to the Hawaiian volcanoes here on Earth, but there's no water burying its base. So here you can see that it's flowed way out. It's, I believe, larger than the entire state of Missouri for scale. So quite large. So that's some of the mapping that you can do with some of our data that we've got in entity value. Some additional mapping that you can do here. Here you can see that I've extracted the all the lunar maria in the solar system. So this is actually an entity class. It shows up as a yellow box. So just like everything else, I can hit Shift Control Enter to format it. And so you get your lunar maria. We're going to get the coordinates and the sizes for everything. And then you can actually plot where these things are. In this case, I've actually used a particular projection to see the entire moon. It's a Molvida projection. I believe I'm pronouncing that correctly. And you can actually plot the various lunar maria in different colors to make them all distinct. All right, moving on. So we can also do 3D regions. So if you, geographics is nice for just general maps and things like that. But if you ever wanted to do actual calculations with like solar system features, craters, things like that, you can actually do that. So here, we've got another example where we've done geographics once again, in this case for the Copernicus crater on the moon. And we're just doing an orthographic projection, so it almost looks like you're looking at the moon itself. But you can actually request elevation data for the moon. And in this case, we're restricting it to about the size 1.5 times essentially the diameter of the crater itself. And we're getting that elevation data. And then we're requesting that geo-elevation data give us a region. And what you get back is a region that you can then feed into the same frameworks that we have for doing general region computation for what I think up to this point has been mainly demonstrated for mathematical regions for the most part. But you can actually use the same exact frameworks on this particular data set. All right, I'm going to move on from that. We have a lot of other areas to cover. You can also do surface plots. So here's another example from Mars. Mars is very topographically interesting, so it's kind of a nice example set. We've got Candor Chasma. So this is a particular sub-canyon within the Valles Marineris valley system on Mars, which is this whole blue area that you see here. Candor Chasma is just the upper portion, the northern part up here. And you can see that I've highlighted it in yellow using a geo-bounding box. We can extract the geo-elevation data for Candor Chasma, and we're restricting it with a geodisk of 187.5 miles in diameter. And we're going to set some box ratios for scaling purposes. Try to keep it as reasonable as possible. And then we can do a list plot 3D. So we can actually use the geo-elevation data of Candor Chasma to actually plot it and get a 3D plot. You can rotate this like any other 3D graphic and do this for any feature in the solar system, at least for the moon, Mars, and I think Mercury as well. We will be working on some additional data sets for things like Venus. There's not as high resolution data available for Venus, so we're working on that, but the Magellan mission in the 90s might have provided some, and I think we're thinking of incorporating that for Venus as well. So mainly for the moon, Mars, and Mercury, but Venus is coming. I believe Pluto as well. Okay. One more area in the solar system before we move on beyond that. You can see the orbital motions of comets. So here I've shown you've got a comet here. You can ask for the eccentricity. It has a very high eccentricity compared to the planets, which are nearly 0. Comets often have very high eccentricities, closer to 1. And here I've queried for the orbit path of all the planets and for several types of comets. So these are each an entity class. So the Halley type comets, Encke comets, and Chiron type comets. And I'm getting the orbit path for all of those. So I've got the orbit path for the planets and for these different types of comets. And then I'm feeding them into graphics 3D and I'm plotting them and just color coding them. So you can see that the comets out here are highly eccentric and they go way up and you can't even hardly see the planets. They're kind of buried on the inside here. So I'm going to actually just reproduce that so that it's a little bit easier to see them. So here oops, move my cursor and try that again. So here I'm going to get the orbital paths. I'm going to get the orbit paths for these comet entity classes. And then I'm going to plot them. This is a little nicer. I can zoom in this form. You can see if oops, sorry about that. Keep zooming in, you can see the planets are buried deep inside here. With the orange orbits you can see there, but the comets kind of, if you plot all the comets, they kind of, they're all over the place and it kind of creates a rather kind of chaotically interesting picture. All kinds of different angles that they come in from. All right, let's move on from there. Here's something else that you can do. That was a static data, but we also have time-dependent data. So here's an example where I've specified a date range. So we're going from October 15th of 2018 to December 31st of 2018 in 10-day increments. I'm getting comet Wirtanen. This is a comet many of you may not have heard of, but it was actually in the news back around the holidays. And we're getting the helio coordinates. So these are the heliocentric coordinates of the comet over this range of dates. And what I can do is I can plot that along with the planets, and you can see over that range of dates here, you can see at, there's 10 points here for both the Earth and the comet. You can see that the comet made a very close pass of the Earth at that time. And I've kind of viewed it from two different viewing angles here. So the full code there for plotting the graphics is right there. So you can see the scene language that constructed the graphic from the data that we have up above. All right. That's our last solar system example. I think at this point, we're going to move out of the solar system a little bit. We've got quite a few other domains here to cover. Exoplanets is an active area of research. There's lots of new exoplanets constantly being found. We recently had the Kepler mission that was famous for finding lots of exoplanets, but we've also got the new TESS mission that's coming online, and it's already started finding quite a few. We try to introduce new exoplanets on a regular basis to try to keep our data set reasonably up to date. Here you can see where I've plotted all the exoplanets here essentially with their orbital period and their mass plotted, and you can see that you get interesting clustering families. So exoplanets of different types cluster in different areas of charts like this. It gives some kind of interesting what types of planets are out there. So these are ones, the blue ones are ones that typically, they tend to have longer orbital period as the mass goes up. The ones that we've detected, there's some observational bias in here too. So in order for us to detect exoplanets with longer orbital periods, because of the observation runs have a limited time that they can look at, they have to have a higher mass so that they can be picked up and be detectable in the detector. So what you're seeing is probably a little bit of observation bias, that these higher mass planets have larger orbital periods. But there are some shorter, higher mass short orbital periods as well. The low mass planets tend to be found in this shorter orbital period domain. They typically have to be pretty close to their star to be tugging on it fast enough and significant enough to be seen. All right. In the star domain, we have quite a bit of data. We have a lot of stars here. This is another example I'm not going to do in real time. I'm just going to kind of show you because it takes a while to get all the data and to plot it. But you can actually get some interesting structure diagrams by getting essentially a numerical representation of the color of a star. It's called the BV color index. So take a picture of a star in a blue filter, another one a V filter. This is kind of a yellowish green color. And you basically measure that in a CCD camera. You get a brightness value, and you take the difference between the blue and the V are visible. And that gives you an index number. And that's very useful in astronomy. You can also get the absolute magnitude of the star. And if we do that for all the stars, we get the BV color index and the absolute magnitude for all of our stars. We can make use of Ballesteros' formula. This is actually something you can even find in Wikipedia. To convert between BV and temperature, you can actually get the effective temperature or approximate it for a given BV color index. And once we have both, we can plot the color index versus the absolute magnitude and color code based on temperature. So you can see your cooler red stars tend to be on this lower domain. You get the main sequence. These are all the stars right along this diagonal that are burning hydrogen in their core. Once they start burning up their hydrogen, they end up moving off the main sequence, and they move into this branch up into here, and you get the giants. You get the supergiants up here. Let's see, we have a question here real quick. Let me see if I can read this. Even after looking at ref pages and Mathematica Stack Exchange questions on entity, I still can't figure out, is there more to an entity than just an association with keys as properties and a nice display form and some out-of-memory support store? Because the syntax is more complicated than the nested associations in query directly. Not quite sure if I understand the question. Let me see here. Just an association. So the entities themselves are just a symbolic representation. You can get associations out by specifying arguments, like entity association. If you ask for a property, you can say, give me an entity association where I have the entity going to its value. And some out-of-memory support store. You can definitely create your own entity stores. Those are essentially kind of like data packlets that work within the entity, entity value framework, but it's like your own custom data set. So if you wanted to, you could download the data, through entity value for all the properties and entities within a given domain, and then you could use an entity store to essentially create your own local version of it. You can also create entity stores that inherit from known things. So, for example, let's say you don't think that our particular thing. Well, actually, so here's another example here. Oh, I think I know what you're asking about, but I'm not sure. Let me see. So here's what you typed in. So you're saying, why doesn't something like this work? You mean, I assume by this, you mean something like, why doesn't the string work as opposed to the entity? The problem is that strings are not unique. For example, Einstein. Einstein could be the person. There's lots of people with the last name Einstein. There is an Einstein satellite. So you need some domain information when you're going to ask for things like the mass so that you can give some context to the question. So something like Jupiter mass by itself, that's fine, but in your head, you know that Jupiter is a planet, but the system doesn't know that. There could be something else called Jupiter. There's Jupiter rockets, and are you asking for the mass of the Jupiter rocket? What are you asking for? So this is why the entity framework tells you what domain I'm talking about, planet. Now you've given some context here, and so now it knows what you're talking about. Let's see. No, if entity Jupiter is simply an association. You mean you want to get all the properties for Jupiter? I'm assuming that might be what you want. I think you can do that with entity value. I know there's a way to get this. I think this will work, but let's see. Yes, this works. So if you wanted to get all of Jupiter's values, you could do this. It takes a second to download and format all the data because there's quite a bit of data that we have for all the properties of Jupiter. This includes some 3D graphics. It includes the orbit path. There's a whole bunch of stuff that comes back here, and you can see that it comes back. So all of it comes back as an association here, telling you the property and the value. All right. So let's see. I'm not as familiar with query. I'm going to move beyond this question. This seems like it could get complicated, and we could spend a lot of time on this. I personally have not used query myself, so I don't want to speak too much toward query, but I will try to play around with that a little bit afterwards to see if I can figure out what that is. All right, let's see here. Something else that I'm going to show here real quick before moving on from stars here is, this is another variant of the this is called a Hertzsprung-Russell diagram, or a color magnitude diagram in this case. We're going to see where we have some kind of data bias here. We have most of our data in this this portion of the main sequence. As you start getting into the tail, you get very low mass faint stars, including down into the brown dwarfs. And here you get a lot of giants and stuff. Other types of stars are less sparsely populated. There just aren't as many of them known. They're rarer stars when you get into the really high masses. Okay, so let's see here. This is another visible example here for stars. I'm going to kind of move through some of these quicker here. Here I've just got a nice graphical example where I've obtained the temperature of a star. I've written a function here that takes the temperature, the radius, the name, and an offset value for just a star. We'll just genericize that. We're going to have a kind of a unit conversion thing here that gets the entity value for the temperature, the radius, and the name of the star, does unit conversions on it. And then we've got a function that will line these up horizontally, and you can kind of create kind of a nice diagram here. I've actually created a poster. It's actually hanging in my office that has a whole bunch of stars, essentially using this kind of code here. But you can actually create a nice row of stars like lined up side by side, showing how they would compare to each other. So we've got Proxima Centauri. This is the closest star to the sun itself, and then Sirius. This is the brightest star in our sky other than the sun. And you can see how big they are and what their colors are with respect to each other. If you take luminosity out of the equation, in actuality, Sirius would be far more luminous and bright, and it would kind of drown out some of the color. All right, so let's see. So it's just a really basic example here. I'm not going to spend much time on this here. We've got the constellations. So we have all 88 official International Astronomical Union recognized constellations. Here I'm getting Orion, and I'm just showing that you can get the constellation graphic showing you what it looks like in its boundaries. Moving on from that. This is an example. We're getting out into more deep space now at this point, and pulsars are kind of an interesting topic. They're not typically directly observed because they're very, very tiny. They're typically the size of a city, say London, but they're spinning extremely rapidly. And there's a few cases where we've seen the immediate environment around pulsars, and these are basically massive stars that have died. And they're not massive enough to have formed a black hole, but they form what's called a neutron star that spins very rapidly, and it's got magnetic fields. And these magnetic fields are sometimes tilted with respect to the rotation axis. And so here you can see I've kind of shown they've got these radiation beams that come out of the magnetic polar axis. And you can kind of see a representation of the magnetic field here, of kind of an illustration of what a pulsar might look like. But what I'm going to do here is I'm showing that you can actually use audio generator, which is something new in version 12, to actually listen to what a pulsar might sound like. And so here what we've done is for a given pulsar, we're getting the rotation period and how wide its pulse is. Like when they listen to this, as the beam sweeps by Earth, this radiation beam, as the thing spins, it happens very rapidly. We hear a pulse, and you can translate this pulse into audio. And here I've got a famous one called the Crab pulsar. This is in the center of the Crab Nebula that exploded in 1066, I believe, as a supernova. And we can see that remnant in telescopes. If you convert this into audio, you can see how this pulse, how fast it is. It's not a very pleasant sound, but you can hear that kind of very fast, rapid pulsing sound. It's kind of a deep sound. Now, old pulsars, as they age, they slow down, and so their pulse rate gets much slower. And so here's a much older pulsar called Jaminga, and here I'm going to play that. And so you can hear the pulses are much further spaced apart. All right, so that's kind of a neat audio example. Everything's been visual to this point. You can also inspect the range of pulsar spin rates, and you can see that a large number of pulsars are up here. They rotate once per second or faster in some cases. Some really slow ones rotate once every, so imagine something the size of a city rotating, once every second, or in some cases, a crazy number, once every millisecond. And these are your millisecond pulsars down here. Crazy rotation speeds. We can use star clusters. Here you can see that what I've done is in this example, I'm obtaining all the globular clusters and all the open clusters. There's, open clusters are kind of young stars that are kind of irregularly bound together. Globular clusters are very old clusters that formed very early in the universe, and in general anyway, and they have kind of a spherical distribution. They're globular. They're not kind of as randomly distributed. But what's interesting is where they're placed in the galaxy. So here what we're doing is we're getting the heliocentric coordinates for all of them. And I'm going to do a fit to the open clusters, and I'm fitting them to a plane. And here I'm plotting. I'm actually going to. What you're seeing here is that the blue stars clusters here. I was going to do this example, but I think we're short on time, so I'm going to go ahead and just race through this real quick. The blue star clusters here, these are actually in the plane of the galaxy, and the globular clusters are found kind of spherically distributed throughout the galaxy, kind of spherically around it. And what we've done here is we've actually fitted a plane to the position of the blue open clusters to try to locate approximately where the center of the galaxy is. We know the center of the galaxy is at Sagittarius A star, so we've gotten its coordinates here, the Milky Way galaxy, its center coordinates, and so we've offset that fitted plane by that. And so you can kind of see the sun is right here at the center. You can see all the open clusters we know of. Most of them are relatively nearby in the galaxy, and the globulars are kind of more spread out. Okay, moving on. We're getting into space science now beyond astronomy and kind of more man-made stuff here. We've got deep space probes. One thing that's kind of fun to follow is the Falcon Heavy demonstration mission. Elon Musk kind of got into the news by launching one of his cars into space, one of his Tesla Roadsters, and that we actually have information for tracking where his Roadster is at. The official name for that mission is the Falcon Heavy demonstration mission because he was testing the launch of the Falcon Heavy rocket. And so you can actually obtain that by using the entity there. You can get all the planets. And with this code here, you can actually plot the orbit of the Tesla Roadster within the solar system. And actually figure out that in this case, we're actually using a date of September 20th of 2020. It's going to make a close pass of Mars, relatively anyway. It was never designed to actually go to Mars, but it's going to actually make a relatively close pass to Mars in 2020. And it'll just be out there circling forever because it has no fuel left. And here you can see I'm getting a date range. I'm getting the position as a function of time. I'm getting Mars's coordinates and the Roadster coordinates. And I'm plotting its distance, the Euclidean distance between Mars and the probe as a function of time, and plotting that on a date list plot. And you can see how the distance between Mars and the probe varies over the next few years. Here's that minimum distance over there in, was it October? What was it? I think October 2020. No, September 2020. So September of 2020 is when the nearby thing is going to happen. All right, moving on. Tracking satellites. If most people want to track the ISS, it's actually very bright. If you want to know where it's at, you can actually use code like this that's on this marketing page to figure out where the International Space Station is at and which direction it's heading. And with version 12, we've even got some new formatting options that in this case, we're making use of. I'll just copy and paste this so that you can see the code that we've got hidden in these options here. So you can see we've actually got geoprojection, vertical perspective, and you can have the center be somewhere other than where you're hovering over. So it can give you kind of this offset look. And you can see the position of the ISS at the time that I specified and evaluated this graphic, where everywhere in this orange disk would be able to see the ISS. It's moving along this path, kind of makes it look like it's a 3D graphic when in a sense it's just geographic, so it's still 2D. It's a nice visual effect that you can create. All right, a couple more things here. To wrap up, we've got creating maps of lunar landing sites. So here we're making use of manned space mission to get the Apollo 11 manned space mission, and we're getting its position. So in this case, it returns a geoposition object. We can feed that into geographics and plot where that's at on the moon, so you can see where Apollo 11 landed, both with a satellite imagery as well as with a relief map. Specified just as the geo background options to geographics. All right. And I got one last example here. Something that's it's useful information to have. There's not a lot of data that we have for these things, but it's nice to know where these observatories are because sometimes you may want to use them as an observation location. And as we talked about at the very beginning of this presentation, I mentioned that you can have an observation location specified for a given astronomical object. So if you want, you can actually use, for example, Kitt Peak as an observation location. And so we do that by obtaining the geopositions of those things. And here you can see we can plot that on geographics and show you where Kitt Peak is, that's in Arizona. You can actually get all astronomical observatories, get their position represented as an entity association. And we're going to get rid of the ones with missing coordinates. And then what we can do is we can arrange those and extract out only those that are within North America. So rather than all the worldwide ones, we want to create a map just showing the ones in North America. So you can use pick to do that and geo within Q, and you get the following graphic. So you can see where all the observatories that we have data on so far. I think we have plans to expand this to include, there's an amazing number of observatories, and many of them are very small. And there's actually much larger data sets. I think we're planning to incorporate a lot more. So if you're wanting to observe from any one of these, it will be useful to have that data. So this has been a very kind of generally broad overview of all the different areas. This isn't even all of them. We have others as well. I mean, we have nebulas, we have galaxies, we've got radio sources. And these are just some of the ones that were a little bit easier to create nice visual examples for presentation purposes. So with that, I think that's mainly the end of my presentation. So I don't know if there's any other additional questions. I know we had some early on. Once again, I'll have to investigate query. I haven't actually used that personally myself. I'm much more familiar with entity value directly, but I'll investigate query. Thank you for drawing my attention to it. It sounds familiar. I'm just not placing it in my head right now. All right, not seeing any additional questions. So, all right. Well, thank you everyone for attending, and hopefully you will have fun using these as a basis for your own explorations. And hopefully, if you share things like this on community, I occasionally post there myself. So take a look there. I've created some flybys of Saturn and things like that in the past. So feel free to use these as a basis for your own post to the Wolfram community, community.wolfram.com. And I will hope to hear from you all soon. Thank you.